Each floor of the chip has its own blueprint. How do we draw it? Perfectly every time? Welcome to lithography. After deposition lays down a fresh layer, lithography is what prints the pattern onto it. Every modern chip needs dozens of these blueprints. In the fab, we call the result a stack, layer on top of layer, each printed with its own pattern. Get the stack right, and the chip works. Lithography means printing a pattern onto the wafer using light and a mask. The mask is the blueprint, the pattern, for one layer of the chip. Light shines through the mask. It projects the pattern onto a thin coating on the wafer called photoresist. Wherever light hits, the resist changes. In the next step, some parts will wash away. Other parts will stay. That difference is the printed pattern. Every layer of the chip goes through the same four-step loop. Step 1. Coat. A small puddle of liquid photoresist is dispensed at the center of the wafer. The wafer spins fast. Centrifugal force spreads the resist into a uniform film, just a few hundred nanometers thick. Step 2. Exposure. The wafer enters a scanner. The mask is loaded above. Light projects the mask's pattern onto the resist. The light is either deep ultraviolet at 193 nanometers or extreme ultraviolet at 13.5 nanometers. Step 3. Develop. The wafer is sprayed with a chemical that washes away the exposed resist. The pattern is now physical. Raised lines and trenches in the resist, ready for etching. Step 4. Hard bake. Bake the wafer to harden the remaining resist. The pattern is now durable enough to survive the next step. Repeat this loop dozens of times. Every floor of the chip needs its own blueprint, and every blueprint goes through the same 4 steps. 2 knobs decide whether the exposure step actually works: focus and dose. Focus is how sharply the mask projects onto the resist. Just like a camera, the light has to focus at exactly the right depth, off by tens of nanometers, vertically, and the pattern blurs. Edges go soft. Line widths shift. Dose is how much light energy hits the resist. Think of it like exposing a photo. Too dim and you can't see the image. Too bright and the lines blow out. Photoresist has a sharp threshold. Modern recipes run within about 2% of the right dose. Get both right. Every shot, every wafer. Or the pattern is wrong before it leaves the scanner. But here's the question. Once the pattern is printed, how do you know it's consistent? Same line width as yesterday's wafer, same as the wafer next to it on the production floor? And did the pattern land directly on top of the previous layer in the stack, or shift by a few nanometers? That alignment between layers, engineers call it overlay. Don't know equals failed. 3 tools answer the question. First, critical dimension scanning electron microscope. The fab's microscope for measuring how wide each printed line came out. Second, overlay metrology. The alignment tool required precision, a fraction of a nanometer. Third, defect inspection. The wafer-wide scanner that finds contamination and pattern errors. 3 tools. 1 question. Is the pattern consistent? Before a lithography recipe ships, it has to clear 5 gates. 1. CD uniformity. 2. Overlay error. 3. Defectivity. 4. Focus and dose. 5. Sign off. All 5 green, the recipe ships. 1 red, the tool comes down. The pattern is printed. Now we cut. But how do we prove the cut is right? Not just to us, but to the customer? Next up, etch. If you work in a fab, here's the question that decides how a lithography process gets managed. Why is 1 minute of scanner downtime 5 times more expensive than a deposition tool? 3 reasons. First, the capital. An EUV scanner runs over $200 million. The newest models pass $350 million, 5 to 10 times what a deposition system costs. Second, throughput. Every wafer in the fab passes through lithography more than 50 times. The scanner isn't on the critical path, it is the critical path. Third, when the scanner stops, every downstream tool starves within hours. That's why a lithography recipe lives or dies on overlay.